Okay, so basically I'll kind of pick up from where Ali left off. And Ali sort of explained to you in the last two lectures, sort of two very different looking formalisms, right? One was this idea of like array structures, and the other was this formulation of topological recursion. One was like very algebraic, right? It had some differential operators and so on. The other one was kind of more, well, geometric, complex analytic, however you want to think about it. And what I want to start off today is to explain how these formalisms are basically related. I mean, or to be more precise, that topological recursion is sort of an example of an array structure. So sort of the first thing that I want to do today is to explain to you that topological recursion is an example of an array structure. Okay. Yeah, before I do that, let me also say then after, so after that, kind of what I want to mostly focus on today and the lecture tomorrow is to talk about why topological recursion is useful somehow. So I sort of mentioned this already in his first talk, that there's lots of different enumerative problems that are sort of governed by topological recursion. But it's not just that these problems are governed by topological recursion. There's also connections to integrability, so there's all these kind of different connections, and you can use tools from one to maybe get something else from the other. So, and I'll try and really focus on kind of three, let's say, applications, which are going to be about Hurwitz theory, KP integrability, and relations to the moduli space of curves that we've seen in those lectures. Okay. Okay, so let me start by doing this. So this is somewhat technical, so I'll try and be brief and sort of just give you the idea of how you would go about proving something like this. And how you should do this is using this idea of loop equations. Okay. And so I'll write down what these loop equations are in a second, but where do they come from? So they sort of come from where the origins of topological recursion come from. So they come from matrix models. And we've kind of seen them in some form in Valentin's lectures, where he kind of wrote down these various error constraints, and they essentially, where he was explaining how you can get this kind of recursion on graphs by sort of removing edges, and you look at what happens. There's this kind of, it splits into different things. And that's kind of where the loop equations are coming from, okay? So sort of coming from matrix models or maps, whatever. But one can formulate it so purely in terms of the data that you've seen in topological recursion. So let me do that. So let me consider some collection of differentials, omega gn, on a spectral curve. So there's two loop equations. So the first one is called the linear loop equation. And this one says that if you take omega gn of z, then I don't care about the rest of the variables, so z2 to zn, so everything's going to be happening in z. I take this kind of involution that Ali defined, right? This was this local involution at the ramification points. So it says that this guy is holomorphic near z equals a, at z equals a, where a is the ramification point. Okay. This is not automatic, right? So we saw already in some examples that these, and maybe I'll explain this as a general result, that the omega gns that you'll get from TR, they have poles at the ramification points, right? So the point is that when you take the sum, that the poles should cancel out. Okay. So it's the first loop equation, the linear loop equation, and there's a quadratic loop equation. So this one is it's a bit uglier. Oh, sorry. Maybe I should let me divide by dx of z. So as a function. Okay. And let me write the quadratic loop equation here. Okay, this one says that if I look at essentially the stuff that's like appearing in the topological recursion formula, so there was this omega g minus 1 and g minus 1 n plus 1 z signal of z, and then stuff z2 to zn, plus the sum over g1 n1 plus 1 z so yeah, so here's like the usual sum, so it's like sum over g1 plus g2 is g, n1 plus n2 is n. Okay, and yeah, so this guy, so it depends a bit on whether the ramification point that we're looking at, the one A, is of type Airy, is of Airy type or Bessel type. So these kind of two different cases. Basically, it says that it's holomorphic at A if Airy type, if A is of Airy type, and it has a double pole, at most a double pole. If it's Bessel type. Okay, so this is like almost the thing that you saw in the topological recursion formula, except that maybe I should point out that here there is no prime. So omega 01 is included, okay? Which it wasn't in the topological recursion formula. Okay, that's the only difference. Okay, and what's the point of these things? So basically, what you want to do is like now you want to ask for the space of solutions to these equations. Okay, so obviously they're not like, yeah, you can see that somehow they're not determining. Okay, so the question is, what is the space of solutions to the loop equations? Okay. Oh, so maybe I should say that, you know, I'm not assuming that these omega gns are defined by topological recursion yet. So I'm just giving some constraints on what these omega gns are, what these omega gns should satisfy. And I'm asking like, oh, what is the space of solutions to this kind of set of equations? Okay. Yeah. Oh, I could do it or not. It doesn't really matter for the same reason that these are irrelevant. So yeah, I mean, I could, but I don't know. RAM is RAM plus if you want. Yeah, it really doesn't matter. Yeah. Yeah. So you see, this has two copies of Z appearing, right? So it's like a quadratic differential in Z. So I'm just dividing by dx squared to make it just a function. And here it's just once, so I just divide by dx. Okay. Okay, and the cool thing, well, yeah, and the cool thing is that somehow, given these kind of constraints, plus a bit more, the topological recursion constructs the unique solutions to these loop equations, okay? It's not quite true, because what one can do is like sort of add holomorphic, just like purely holomorphic terms to the omega gns, and that's not changing the loop equations. You can kind of see it, right? If I just add purely holomorphic things, nothing's changing the loop equation. So the general space of loop equations, I mean, it's also known. It's called the blob topological recursion. I won't talk about this at all, but it means that you can add, yeah, you can add holomorphic terms, purely holomorphic terms. Okay. But what we're going to, what we're going to talk about is so what we're interested in is the set of such differentials that satisfy the loop equations, but also satisfy this additional property that Alessandro introduced, which was this projection property. Okay, so as soon as you impose the projection property, remember that was somehow reconstructing your differentials purely from the polar parts of these differentials of the omega gns, right? So as soon as you impose that, basically kind of these holomorphic kind of ambiguities sort of go away. Okay, so that's the theorem. Is that topological recursion topological recursion constructs the unique solutions to the loop equations that satisfy the projection property. Okay. So the idea is that the loop equations basically fix all of the kind of principal parts at all the ramification points, and basically once you introduce this, once you ask for the projection property, it basically extends it globally to everywhere. Okay, so there's none of these holomorphic things happening anymore. Okay, so that's kind of a nice result, right? That's sort of like the origin, if you want, of the modern viewpoint on the origin of topological recursion, if you want. Okay, and why did I introduce this? The point is that, okay, so now we saw, so that from TR, right, one can get TR as like solution to the loop equations, the solution to the loop equations with this projection property. And the loop equations, you can realize them as some kind of differential constraints. Which then you have to work a little bit harder to show that it's an Airy switch. Okay, and let me tell you the idea of how this goes. Are there any questions about this so far? Good. Okay, let me tell you how this goes. Where is this? Okay, maybe I'll be smart. Try to not write too much more. So okay, there are a few steps. So the first step. Okay. Maybe I want to say one more thing. Okay. So the first step is somehow to turn these. So remember that there were these like FGNs that were appearing in the array structures, right? So somehow the idea is that you want to extract the FGNs, these kind of some numbers from these differentials, and you do that by expanding in some basis of differentials. Okay. So the first step is that I expand omega gn in this basis of differentials that Alessandro introduced, these ck of z, some basis of differentials. Okay. So let me use the following notation. Oh, so this notation is somehow a little bit different from the one that, okay, sorry. For showing this, I'm going to assume you don't have to do this. It just makes all the notation like simpler. So assume that the spectral curve only has one ramification point, has a single ramification point. Okay. So this is just to make what I'm writing everything just simpler. Like everything goes through. This is not really important. Okay, so yeah. So this notation is a little bit different, but I sort of prefer to use this notation. So I'm sorry about this. I'll just use bad notation. Okay, so I expand in this kind of basis of differentials. I get some kind of expansion. This is a finite expansion. Okay, so only finitely many of these guys are non-zero. Okay, and this was a consequence of the projection property. Okay. Okay, and then the second step is that now that I have these linear loop equations, these loop equations in terms of the omega gns, I want to turn them into some kind of residue constraints, which essentially will give me some relations between these FGNs. Okay, so how do I do that? Well, okay, this is holomorphic at the ramification point. Well, another way to say that is that if I multiply this by, let's call it CK of Z. I don't remember if Ale introduced this notation or not, but this is like the holomorphic parts, right? So this is like, if I choose some local coordinate, rho, let's say, something like that. Okay, and I take the residue, z equals 0. I mean, this guy should be 0. For all k, that's at least 1. Okay, because I don't have any poles, I'm just multiplying by some power of this local coordinate rho that's centered around the ramification point, and I take the residue, so I should get 0, right? Because I don't have any poles that are contributing. Sorry? Residue at A. Yeah, thanks. At A. Yeah, so I've just one ramification point now, single ramification point that I call A. Okay. And rho is just a local coordinate centered around A. Okay, I do the same thing for the quadratic loop equation. Oh. Okay, so it's 0 if it's of Airy type. Okay, if Airy type, remember, is holomorphic, so it's going to be 0 for all k that's at least 1. And if it's of Bessel, then it could have a double pole, right? So I have to start at least k equals 3 to not see this pole. Okay. All right, so far so good. Okay, now what should I do? I should basically kind of expand these omega gns in the basis of differentials, right? That I have. I should use this expansion that I have here, plug it into these formulas, and that's going to give me some relations between these FGNs, right? Okay, so now these are the steps that I'm not really going to write out. So maybe, okay, or let's say as a consequence of these, I get a set of relations between the FGNs. Okay, now this is some algebra, right? Okay, you get this set of relations between the FGNs, and you want to realize them as the set of relations that was coming from an Airy structure that Ale wrote down. So you had something like FGN equals some stuff that had lower Euler characteristic. Okay, turns out you can do that, and I'm not going to do this explicitly. So maybe kind of the last step. Conclude this proof is, well, I'll define my Z, which I want to be my Airy structure partition function, the exponential, h bar to the 2g minus 2 plus n, or in factorial. Basically a generating function of these FGNs, okay? Okay, and I claim that one can realize the relations between the FGNs that you got here, realize these relations as coming from this kind of set of differential operators, some set of differential operators that I'll call HI acting on Z, where let's say, I don't know, I starts from some index, I is in some index Z, so let's say starts from 1. I'm not telling you what HI are. Okay, and a good exercise, if you don't believe me, is to do this for the Airy curve, okay? So do this for the Airy curve is very, very simple. What you should get here are the Versero constraints that you get for the Kontsevich-Witten partition function. So the exercise, do this for the Airy curve. Okay, and maybe sort of the last step to sort of conclude the proof is to basically check that these are not just any differential operators, but they're actually some differential operators that form an Airy structure. Okay, so last step, check that HI form an Airy structure. Okay, and what you'll see is that these HIs, they're always going to be some Versero constraints. They're going to be different ones based on if the ramification point is of Airy or Bessel type. Okay. So these HI, it's always a representation of Versero. Well, half of Versero, so maybe width or Versero plus, maybe. Yeah, and so in fact, because Ali already showed you what these guys look like, you can check that they form an Airy structure from the Versero commutation relations, essentially. Yeah, maybe just to say, I mean, they're different for Airy or Bessel, for Airy, Bessel. And kind of, you know, you might think, well, that's actually only the simplest examples that we had of the spectral curves, right? There were some that were like much more complicated than the Airy and the Bessel types. But actually it turns out that the operators are just conjugations of the ones that you get for Airy or Bessel type, but by some of the other stuff that's happening in omega 01, omega 02. And the point is just that like locally, if you look at a spectral curve, right, like they're always around the ramification point, it always looks like Airy or Bessel. And then there's some, you know, maybe some other stuff that's happening, but like locally, it always looks like Airy and Bessel. And the way that the way that you see that, like on the Airy structure side, on the algebraic side, is just that you always get the Airy or Bessel type differential operators, but then they're just conjugated by some other stuff. Okay. Okay, and maybe okay. So let me write this as a theorem. So this is, I suppose it's, yeah, it's kind of, well, it's due to Kontsevich-Tillman, but also, I mean, maybe written more explicitly in this paper, in a paper of Anderson, Boro, Chekhov, Oranta. Is that, I don't want to write it compactly. Okay. Okay, so maybe I'll just write it like this: Z here, Z defined here. Yeah. So the expansion coefficients of the omega GN on any spectral curve with simple ramification points. I mean, the simple ramification points is important here. which I call FGN as before, are the coefficients of an array structure partition function where this array structure is constructed using n, let's say my spectral curve has n simple ramification points using n copies of the Versor algebra. Okay, let me draw a picture. I mean, so there's some nice kind of relationship between kind of the geometry of the spectral curve and this kind of Versor representations happening here. So basically, your spectral curve, I'm assuming that it has simple ramification points. And you should think of as like around every simple ramification point, there's like a copy of Versor algebra. And somehow all these copies are sort of glued together in some way to give you basically the topological recursion formula. Okay, so that's kind of what topological recursion is, if you want. So I mean, yeah, just I don't know, schematic picture. This is my spectral curve, right? Sigma mapping to P1. Around each of these simple ramification points, I have a copy of Versor. Okay, and topological recursion is basically telling you how to. So these a priori don't talk to each other. So they're just different sort of representations. And what topological recursion is like it's telling you how to glue these Versor representations into this kind of topological recursion formula. Okay, if you want like topological recursion, is a gluing of Versor reps at ramification points using the geometry of the curve. Okay, any questions? Yeah. So yeah, it does, right? So basically, yeah, what changes is that I told you, so I mean, I told you that the omega GNs are like an expansion. I mean, the FGNs are obtained as an expansion of the omega GNs in this C basis. And there I was using the projection property, right? Because I said, like, oh, the omega GNs, if you expand them in this basis of differentials, I get this kind of finite expansion where I have these FGNs. So if you added just some holomorphic parts, like it wouldn't satisfy the projection property anymore. And so that's kind of where I'm using the, yeah. Yeah, I don't know, but I think that, I think that there's some way to realize, like, so I don't know about this, but I don't know, Swagata maybe knows, I don't know if he's here. But like, there's some way to kind of realize blob topological recursion also has some kind of like generalization of array structures called like partial array structures or something like that. So basically it's something like, if the array structures, I mean, there was this kind of like uniqueness condition where you were kind of fixing all of the dependence on the, so there was this uniqueness condition which said that the operators, they needed to start like h bar d over d dxi times plus some higher order stuff, where all of the i's that are, the variables of your space like appear. But you can sort of somehow relax this assumption to not fix all of these i's, so you'd only have some operators that they don't necessarily fix all of the dependence on the xi's, and this kind of extra dependence in some way you can see as coming from this kind of blobs that appear in the blob topological recursion formula. That's like a very rough idea. But, yeah. Sure, every curve fits into this. Yeah. Airy. Yeah, it has, I think it has three ramification points that matter, and they're all airy type. Okay, good question. Maybe I should have said something about it. Good question. So, right, so Virasoro is like very, very strongly related to the fact that I have simple ramification points. And somehow the representations that you construct of Virasoro actually also use the fact that you have these simple ramification points. If you drop that condition, what you would get are instead like these kind of W algebra representations, which are sort of these higher, I guess they're kind of vertex algebras that are kind of generalizations of Virasoro algebras. So yeah, basically the fact that, so Virasoro, let me just say this. You can think of this as a W algebra of SL2. And kind of where the SL2 is appearing is in the fact that it's simple ramification, so there's kind of two sheets meeting together. And if you had like more sheets, I don't know, D of them, then you'd get just the W algebra of SLD. So a lot of the story sort of goes through as well, but I decided not to introduce it for the sake of not having to talk about what W algebras are and vertex algebras are. It's just, the definition of a vertex algebra is like, I don't know, it's like 2 pages long, so rather not introduce that, so. Okay. Okay, if there are no more questions, then I think that we can talk about some applications. Okay, so now we've seen array structures, we've seen topological recursion, we've kind of seen how these two things are related. One can go from one to the other. And now I want to talk about some applications, like why is this useful? Why we spent like the last, I don't know, like 3 and a bit hours like talking about this story. It's because it's useful to compute a lot of things. So, sorry, maybe there's one important thing that I did not mention. So sorry, before I move on. So corollary of this theorem is in fact that these omega GNs that are defined, if you want, by the topological recursion formula are symmetric. Okay, so there's a way to prove symmetry using in this case that we've been talking about with simple ramifications. There is a way to prove that the omega GNs are symmetric somehow brute force. So you just kind of use the recursion formula and you do some like contour integral manipulation magic. But if you want to do that actually in general for these kind of W algebra cases, this becomes like an absolute nightmare. And so a very nice consequence of this kind of array structure story is that you get for free that the omega GNs are symmetric differentials. Okay. So maybe I should write that because it's sort of important. So corollary of that theorem over there is that the omega GNs are symmetric differentials. Okay. And somehow the work that you need to do in proving symmetry goes down to understanding these operators. This essentially boils down to the fact that these operators give you an array structure, right? And then the kind of theorem of array structures tells you that the FGNs are symmetric, so then the omega GNs are symmetric. Okay. All right, so now let's do some applications. So I want to spend my time talking about basically 3 applications. And a little bit about how they will sort of interact. And we'll see hopefully in tomorrow's lecture that they all sort of interact with each other. Okay, so the applications that I want to talk about are to Hurwitz theory, to the modular space of, to KP integrability, which we've seen. Both of these things we've seen in Valentin's lectures. And And the last thing is about the modular space of curves that we've seen in Dhruw's lectures. Okay. And hopefully at the end, I'll sort of work out an example where you'll see how these kind of come together. Okay, so let me start by telling you what the statement is for Hurwitz theory. Okay, so remember that Valentin told us about this kind of generating function that was this that had these shores, right? So something like your sum over all partitions, you have shores, fund of P, and this kind of product over contents. I got H bars in the right places. The only thing that I've done is like, this is the formula that Valentin showed us, right? C is the content. This is just some Schur functions, and I've added some H bars to keep some, I want some other parameter that's kind of keeping track of this genus. So I've added these H bars. Oh, where G was the weight. So G's usually called the weight in weighted Hurwitz theory. So when G was just like a linear polynomial, right? When G was linear, you get the story of maps. When G is quadratic, then you get bipartite maps. And one case that's maybe important is when G is exponential, you get simple Hurwitz numbers, what I call simple single. Alessandro talked about this as well. Where this is like where you're kind of keeping track of like one partition that's maybe over 0 or infinity, and everything else is just simple ramification points. Okay. Oh, this guy has an expansion as follows. More G and N. Some more partitions of length N. And these P's are the power sum variables. So I mean, this is all the stuff that we've seen so far. And the theorem is the following. If you put all of these H's into a generating function in the following way, if I put all of these HGNs into a generating function, as follows. Sorry, let me say it differently. If I look at this following spectral curve, so first of all, I assume that let G be either let it be an exponential times a rational function. Okay. Then I look at the following spectral curve. My sigma is P1. I take X to be Z over G of Z. Y to be basically Z over X, or Z over X of Z. And omega 02 to be the standard Bergman kernel, so dz1, dz2 over z1 minus z2 squared. And compute the TR differentials on them, okay? These are called omega GNs, right? Okay, now I expand these differentials, not in the basis, this C basis that we've seen so far, but in sort of in different coordinates, okay? I'll expand them near Zi equals 0. In the local coordinate that's given by X, okay? So it's going to be a collection of numbers that I will write, so x of z I to the mu I minus 1 times mu I, maybe. Okay, so product over all I. Okay, so I'm expanding these differentials in this local coordinate x around z equals 0. And the coefficients that I get are exactly the Hurwitz numbers. These guys here. Oh, times some automorphism factor. It's not important. And I sum all the units. Okay. So this is a theorem. This is a theorem. So yeah, I mean, this theorem has sort of a long history. I mean, various cases of G where, correspond to sort of more classical Hurwitz numbers that people have studied for a long time. And this was proved for various cases, but sort of a uniform proof of this theorem for any weighted Hurwitz number G was given recently in a paper of Bychkov, Dunin-Barkowski, Kazarian, Shadrin. Missing someone? No, got everyone. Good. And building on some other work which was done for when G was just a polynomial by Alessandro, Chapuis, Enad, and Hanan. This is fairly recent. But I mean, this problem for when G is classical. So like for simple cases like something linear or quadratic, or this exponential case was done much before by various people. So there's a long list of people before this. So maybe I'm not going to prove this theorem. I mean, this is kind of using some pretty hard algebra, let's say. But the main tools that they're using is using this like fermionic Fock space and kind of the operators on this fermionic Fock space. And for people that know about these kind of Okounkov-Pandare-Pandey operators that appear in these Gromov and Hurwitz papers. So I mean, they're using a lot of this kind of Fock space technology to prove this. Oh, there's also maybe I'll just mention that there's also, if you don't like the Fock space, but you should. There's also a proof that kind of uses like kind of some W algebra representation theory that we gave in a paper with Maciej and Kento. Okay. Okay, so it turns out that, I think someone was asking this earlier when Ali was talking, that basically all kind of reasonable Hurwitz numbers that you can think of that where you're only keeping, that are sort of single, so you're only keeping track of one of the partitions, is computed by topological recursion. Okay. And I mean, from the Hurwitz point of view, I mean, maybe it's a bit surprising, right? I mean, why would you expect that if you put everything into some kind of generating function like this, that you get some differentials that have very nice properties, right? That have only like poles at the ramification points. That's something very simple. So that's quite surprising from like the Hurwitz theory point of view. There's no reason to expect something like this. Okay. So from like a combinatorial point of view, I think that's something that's quite surprising that you even get a generating function that's like, I mean, because you're putting it together like in this variable x, right? But then in the end, you end up with like some kind of rational function in Z, or rational differentials and meromorphic differentials in Z. So that's kind of surprising. Okay. So that was Hurwitz theory. Okay, very good. We'll come back to it later, but let me talk about KP integrability. Are there any questions about this? The statement makes sense, right? Hopefully the theorem makes sense. Okay, something else. I mean, this is a very general theorem, as you can see, and for the relation to KP integrability is yeah.
Is part of this theorem also
not yet, but it is a consequence well, yeah, it's a consequence of this theorem and the fact that there's this connection to the Maciej curves that I'll get to later on. Exactly. Yeah. For every for every spectral curve, there is a coefficient in the background. I mean, I'll explain this later in the next lecture. But yeah. So a consequence of putting together the connection to Hurwitz theory and Maciej curves is that you get an ELSV type formula for any of these weighted Hurwitz numbers. Proof? Oh, of course, has proofs. Yeah. Yeah, I think I don't know in this kind of generality if there's any kind of non-TR proofs. Yeah, in fact, I don't know, other than the kind of usual VLC formula when you're working with simple Hurwitz numbers, I don't know if there's some kind of non-TR proof really. Yeah. So yeah, it's kind of quite a powerful result. Yeah, I don't know. I mean, I'm not sure if I should say this, but like, when Sergei Shadrin is like giving these kinds of talks, he's basically saying something like, so I haven't really understood the statement, so I'm just going to repeat it the way that he's saying it. He's basically thinking of TR as like, there's some kind of like like some sort of like localization that's kind of happening on some kind of master space, but you don't really know what the space is, but you just in the end get the result of the localization, which is the ELSV formula. So yeah, this is, don't criticize me for this statement. It's not coming from me. But I think there's some like moral argument maybe that you can make like this. Okay. So KP. Yeah. So let's. Yeah. So I mean, I'm sort of presenting some of the applications that are sort of very general, right? So you can see that this is like kind of happening for any Hurwitz numbers. You'll see that for the KP integrability as well, and the Maciej curves. I mean, all of this like sort of very general. There's sort of more, applications that are like restricted to various settings, but I chose to present to you like the ones that are sort of very general. So. Okay, so yeah, let me take some spectral curve. I just asked that it's compact. So sigma is compact, proper. Genus 0. Okay, so it's just saying that sigma has to be P1. And omega 02 has to be dz1, dz2 over z1 minus z2 squared. So the standard one. Sort of not made the best use of the board. Yeah, let me go back there. Yeah, so basically the statement is that if you compute the omega GNs on some on any genus 0 spectral curve, you will always get some KP integral differentials. Okay. So the statement is that, so I expand my omega GNs now at some regular point, okay, at a regular point. So a point where the omega GNs don't have poles. And we know that they only have poles as ramification points, so you can pick your favorite point. For instance, here we pick like z equals 0, but pick whatever. In some local coordinate, in a local coordinate, it's okay. So if I do that, then I get something like this. I get some numbers, call it f k1 to kn. Okay, so it's basically, I mean, if you want, it's like kind of exactly the same thing that the expansion that I did here, except that I'm just doing it at any point, and not necessarily for curves that are of this type that are coming from Hurwitz series. And then I build a kind of generating function using these f's. I call it tau, p1, p2, and so on. Some more GNN. I guess I should keep track of the genus as well. Okay, so I basically build a generating function, take the exponential, should put h bar. Is a tau function for the KP hierarchy. Okay, so basically, I mean, this is kind of, I don't know, like an amazing theorem, I think. Like, so if you basically compute omega gns on like any spectral curve that you want, like, so you can choose x and omega 0, 1 to be whatever you want. You compute the omega gns, you expand them in any local coordinates. So you can take the same curve maybe and expand them to like different local coordinates, right? Different points, but at different points of expansion. So at a regular point, yeah, whatever. Turns out that you always get a KP tau function. Okay, it's kind of cool. So in particular, if you want, as a consequence of what I told you about Hurwitz theory before, right? I mean, this was also an expansion in a local coordinate near z equals 0. You can see that this, I mean, in some sense, like if you put together this theorem and this, you also see that the generating function for weighted Hurwitz numbers is also a KP tau function, okay, for any weight. Okay. All right, so that was kind of all that I wanted to say about these two applications. Now I'll talk about the application of the Maciej curves, and that's going to be the rest of today and basically all of tomorrow. Yeah. Yeah, so you should not think of it as a Laurent expansion around z equals 0, but as an expansion around z equals infinity. I mean, so it's essentially the same if you want, but infinity is a regular point. So that's how you can put airy into this example if you want. Yeah, so I mean, maybe it's worth saying here already, right? So we've seen examples like, so now I mean, all of the examples that, or few of the examples that Ali gave, right, fit into this. So airy, Bessel, Mirzakhani. Oh, maybe not. What other examples did he give? Mirzakhani? All the weighted Hurwitz ones, right? And so you're getting like loads of examples of KP tau functions that are coming from some kind of enumerative theories. Yeah, it's very specific. Yeah, good question. So it's very specific. If you want to do higher genus curves, the statement is in fact false. So essentially, this is an if and only if. If the spectral curve is genus 0, then you get a if and only if you get a tau function for the KP hierarchy if and only if the spectral curve is of genus 0. If you want to do higher genus, I mean, there's some statements, but there's some kind of stuff that you have to do to correct the tau function. So it's not like the expansion of the omega GNs, but you sort of add some kind of like theta functions and stuff that appear on the corresponding like higher genus curve. And yeah, you have to do something. I mean, it's a bit of a mess. Yeah, but there are some statements that exist in the literature. You want to look at some specific modular forms that come from? Mm-hmm. 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 Sorry, maybe I'm not understanding. So the question is like, if instead, like if as your curve, if as my curve, I take the modular curve, or sorry. Uh-huh. 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 Yeah, that's sort of essentially what I'm saying. So if you do start with a curve that has higher genus, you have to use kind of some theta functions that are kind of living on that curve, like that correspond to those curves. So maybe, or maybe I'm missing the question completely. Yeah, okay. So I mean, in the genus zero curve, I mean, it's because it's genus zero, there's no corrections if you want, but if you're working in higher genus, then there's some kind of theta function corrections. Yeah. Should write a reference. No, I didn't say that. Sorry, yeah. What I said is that if I compute omega GNs on a spectral curve, may or may not be genus zero, these give you a Kp tau function if and only if the curve is of genus zero. Yeah, yeah. Maybe it was sloppy. Yeah. Oh yeah, and I guess I should write a reference. Should write a. Yeah, this is theorem due to Alexandrov and the people that are listed there. So Bychkov, Donenberg-Kovsky, Kazarian, from sort of recently, I don't know, 23 maybe. And maybe it's also worth saying, I mean, so, I mean, a lot of the stuff that they're using is again, the kind of Fock space formalism and kind of this like stuff with vertex operators and these yeah, the boson fermion correspondence and so on. So that plays like an important role in the story, as you would expect, yeah.
So AP is like this some constraint. But here you are also allowing that the spectral curve has modal similarity, which allows for these p-cycle integrals which are non-perturbative.
Yeah.
This is the differential constraints point of view. Is there a way, like, do they have that non-trivial information?
I think that not directly. Maybe it's somehow hidden in the. Yeah, exactly. Yeah. Yeah, I don't think so. I don't think so because, you know, I mean, looking at just the fact that it's a Kp tau function, not really, because you see the Kp, I mean, the equations of the hierarchy are the same, right? So all of these examples are going to satisfy that. Yeah, and if you're asking from topological recursion, or I mean, yeah, can you see some of these kind of non-perturbative effects? I don't know if there's a way to see it other than kind of through resurgence. Maybe I don't know if someone else knows something more specific than that. Okay. Yeah. So, but like, you know, from the Kp hierarchy, you shouldn't expect to see it, right? Because they're the same equations. So why would you get something? Okay, so the rest of, yeah, so as I said, the rest of the today's lecture and tomorrow is going to be just this connection to the modular space of curves. And first, yeah, so for basically to kind of set up the story, I need to talk about a little bit more about the modular space of curves. I mean, it's kind of related to stuff that Dhruv already talked about, but I want to introduce this kind of notion of cohomological field theories. And you've already seen examples of these things, but you haven't seen these words. So let me kind of explain what those are first. Okay. And once we have this, we'll come back to TR. So CoFT for short. This is a very long word. Words. Okay, so these were defined by Kontsevich and Manin, basically to kind of axiomatize the kind of stuff that you get in Gromov theory. Okay. And the definition is as follows. So you'll see that, I mean, this is going to use like the kind of the structure of the modular space of curves is specifically like the kind of strata that's like sitting inside it, right? So the stratification. Okay. So I'll take V to be a finite dimensional vector space. If you're a Gromov theory person, you can think of this as a cohomology of your target. I'll take some pairing, non-degenerate bilinear pairing. And for sort of, well, I'm not sure if it's really much simpler, but at least I won't get things wrong. So I'm going to just choose a basis for E. So I'll just try and write out everything in this basis. So I'll call, if I have eta applied to the basis vectors E mu, E nu, then I'll call it eta. So definition. And because it's not degenerate, I can invert this matrix. So the inverse matrix call it eta mu nu, operator nu. Yeah. Okay, so definition. Okay, co of t on the eta the collection of maps called omega gn from n copies of V to the cohomology of the modular space of curves. Okay. Oh, and in my basis, so if I have something like E mu1 tensor up to E mu n, I'll give this the name omega gn mu1 to mu n. Okay, that satisfies a bunch of conditions. Okay, so the first thing that it has to satisfy is that there is a symmetric group action that's kind of permuting the mark points on this side on MGN bar. And there's a symmetric group action that's just like permuting the copies of V here, okay? And the maps have to be equivariant under this symmetric group action. Or if you want, think of these as like, you know, elements in the cohomology tensor V dual to the nth power, and under the SN action on both sides, it has to be just invariant. So SN equivariant. Okay, and the main axioms are the following too. And this is basically telling you that I don't want just like any random collection of cohomology classes. If I have some reasonable collection of cohomology classes on MGN bar, they should behave well with respect to the geometry of the modular space, right? And what is the geometry of the modular space? There's all these kind of strata sitting inside it. Like as you go deeper and deeper into codimension, which are kind of given by these stable graphs. And so they should behave well with respect to kind of the stratification in some sense. Yeah.
Like that the notation imply that different elements of this vector space, algebra, whatever, can land in different degrees of the cohomology?
Yes. So it doesn't have to be homogeneous. Is that your question? So, yeah. So I mean, if I take different vectors here, they might run in different degrees in cohomology. Yeah. In fact, they might be mixed degree. They might not be pure degree at all. Okay. 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 Yeah, SN equivariance. So kind of the main axioms are the kind of gluing axioms, right? So I don't remember what Dhruv called these maps, or what notation he used for the clutching map. So let me call it like rho. This is the one that takes you from G minus 1 n plus 1 bar, n plus 2 bar, and GN bar. This is a guy where you took like 2 mark points and you kind of glued them together into a node. And the other one, calling it sigma, this is the map that takes 2 copies of your curve and glues them along takes the kind of last 2 points on your curves and moves them along on a node. I mean, it was a long time ago, but hopefully everyone remembers these maps. Okay, and what I need is that if I have my cohomology class omega gn up on here, and I pull it back, it should basically pull back to the corresponding cohomology class on this moduli space. Okay, so what do I mean? So omega gn mu1 up to mu n. Pull it back here, so I should get omega g minus 1 n plus 2 mu1 up to mu n. Okay, but then I see there's sort of two things that I have to put in here. There's 2 slots. Well, I'll just put everything possible. So let's say alpha beta. But then I'll use my matrix, my pairing here, to contract them and kind of take a sum over all alpha and beta. Okay. The only reasonable thing to do. If I demand that my cohomology class here should pull back to the corresponding one there, right? So you know, I mean, this is a collection of cohomology classes, right? And they basically satisfy these relations between them. Okay, one axiom. The other one is very simple. Is very similar. I should do mu1 to mu n1 alpha plus 1. Beta, I kind of use my pairing, somewhere all alpha beta. Okay, and that's the definition. You seem very, very confused, very concerned. Is it hard to read? Yeah, eta to the alpha beta, and there's alpha beta that I'm just summing over. So these are just everything in V, right? It's just some or my basis V1, and then I'm just kind of using the pairing to contract. Same thing here, alpha beta, beta alpha beta. Okay, you should ask about, are there any examples of this? Do you see a definition? And there are. In fact, we've seen a few of them already. Oh, for people that know about coefficients already, I mean, sometimes you also ask for like a unit on a coefficient. But I don't want to talk about a unit because I'm perfectly happy with coefficients that don't have units. So I'm kind of not talking about this axiom. Okay. Yeah, examples. Yeah, so are there examples? So let me give you quite a few of them. So let me give you a bunch of one-dimensional examples. So one-dimensional meaning the vector space is one-dimensional first. Okay, so I'll just use this notation. So I have like one basis element, right? So it's just E1, and the pairing is just defined to be between E1 and E1. It's supposed to define E1. And I take my omega gns and I plug in a bunch of ones. It's all that I can do. I'll just call this omega gn, okay? Just to make my notation easier. Okay, so what are examples? The first one is actually just the unit in cohomology, right? So the guy that sort of corresponds to the fundamental class, right? Okay. That you can see, well, if you pull back under these maps, I mean, you can see what's up. Okay, so this is often called the trivial coefficient. Okay, that's an example. Other examples that we've seen, well, one example that we've kind of seen appear maybe in the Mirzakhani spectral curve or Weil-Petersen volumes is kind of exponential of kappa 1. So this guy, maybe, or the Weil-Petersen quantity. But just maybe you have to think a little bit more about why this is a quantity, but yeah, I'll let you convince yourself. Think about how the kappa classes were defined and what happens under these Dołęga maps to the Hodge the sheaf of differentials. Okay, another example that we've also already seen is the Hodge class. Let me define it as lambda of u. So I just want to keep track of some degrees. So I'll use some degree parameter. So u to the k times lambda k. It's a Hodge quantity. And remember, the lambda is the kth Chern class of the Hodge bundle. Oh, and finally, I mean, yeah, and then one more example, which is kind of the example that kind of motivates the definition of what a cohomological field theory is, or motivated conservation Manin, is the example of Gromov theory. In that case, you just take your vector space to be the cohomology of your target. You take the pairing to be this guy. And you take the Gromov classes, right? So there's the kind of virtual fundamental class. Well, yeah, so I'll take a bunch of classes in here, right? So I'll take evaluation, fallback of some cohomology classes in there. So let me call those V nu I. Cap with this guy, push forward down to MGN bar. This is the map, the forgetful map, the modular space of curves. And this is my definition. Oh, and I sum over basically all curve classes. Okay. This is also good. Okay. Any questions? Oh, sorry. Yeah. Yeah. I mean, omega GN is this. Yeah.
Weil-Petersen EFP
No. You could take exponential of kappa 1, but the role that it plays is that exponential of 2 pi squared kappa 1 is the thing that appears when you're computing the volumes, the Weil-Petersen volumes for the modular space of hyperbolic surfaces with some boundaries. So it's just some convention. So you can put whatever you want here. It doesn't matter. It's not important. Any other questions? Okay, so okay, I have 10 minutes, right? Okay, I want to talk about the given-tile action. So I won't start talking about it now, but let me tell you some why. Yeah, okay, let me tell you something. So I mean okay, so now that we know a bunch of quantities already here, and somehow the idea of the given-tile action is that if I give you a co-of-t, then I want to use like the fact that I have this kind of stratification of the modular space of curves to construct some new co-of-t's, okay? So the idea, use stratification of MGN bar to build new co-of-t's. Okay, this is going to, I mean, when I talk about the eventual action, which I think I'll just start doing tomorrow, I'll just give you the idea now. I mean, it's going to look like a bit of a strange thing. And then after I define it, I'll kind of motivate why this is something that's important and why you should care about this, okay? But the idea is the following, right? Let's say I give you a co-of-t and I want you to build me a new co-of-t using something that you know about the modular space of curves, like maybe some of the cohomology classes that you know on the modular space of curves. So how do you do this? And using the kind of stratification. So let's say I have some strata. I don't know. So let's say I pick this guy. Okay, some strata, genus 1, G1, genus G2. Okay, one thing I can do is, of course, that I know that, I have some cohomology class, right, that's somehow associated to kind of MG1, 2 bar, right? So because I already have a given, so let me say, yeah, so I'm given a co-of-t, right, already. Let me call it omega. So I can build some cohomology class on the strata at least, right? So I can do the following thing. Okay, and then I have to put some two entries. I don't know, let me call it alpha, beta, mu, nu. I'll give these guys some labels. So I put alpha, mu. I do G2, beta, nu. Okay, that's something. That makes sense. But of course, I mean, at the end of the day, I'm thinking of this as like, I want to build a cohomology class that lives on like MG1 plus G2 2 bar, right? So that this is some stratum in there. Okay, so at the end of the day, I should really only, I should only depend on these like mu's and nu's. Or maybe I don't. We call it mu and nu. So what more can I do? I mean, I can put something on the edges, right? So and I want to kind of get rid of these labels of the edges. So let me put some class, some cohomology valued thing that's going to be like alpha, beta, E alpha, beta, using some alpha, beta. So this is some kind of cohomology valued thing. Okay, and I sum over all alpha, beta. Sorry, let me not call these mu and nu, but let me call it gamma and delta. Okay, on the leaves, I can do somehow the same thing, right? I can put something. At the end of the day, I want to get some cohomology class that's like omega tilde G1 plus G2, comma 2, let's say mu nu, okay? So then I can put something on the leaves, on these kind of half edges. I put something like R of gamma delta, gamma mu, or delta nu. Okay, some more, and then I sum over also over gamma and delta. Okay, so I get something on the strata, and I push forward along the kind of inclusion of the strata into the modular space. I get some cohomology class. Okay, of course, if I do this kind of completely randomly, I choose some R and some E's, like I will not get a co-of-t, right? Because why would I? I mean, these are completely arbitrary, right? These are all cohomology valued things. But essentially, this is the idea, and to make this work, I mean, you need various conditions on what you can put on R and E, okay? And this is what the given action is doing. Okay, so given some co-of-t, I'm trying to build some other co-of-t using stuff that I know about my original co-of-t, right, which I'm kind of putting at the vertices, and then I'm kind of going to put some other cohomology classes and kind of some more things that appear here, right? Okay, so this is kind of the rough idea of what the given action is going to do. But I won't start talking about it because I mean this will take me a little bit of time. So so I'll stop here. Yeah. I don't know, and I'm not sure they are. Yeah. I mean, yeah, in this sense, yeah, in this sense, I suppose they are, yeah, to some extent. But not exactly this R and T. I mean, these are going to be sort of cohomology valued, so there are going to be some cohomology classes in the Maciej curves. But some data that you can kind of get out of it, yeah, you can think of as some GL infinity action that's kind of taking you from some point on. Let's say if your original coefficient kind of gave you some k beta function, then you can think of this as like taking you to as a GL infinity action to a point on a different yeah, that's true. Thanks.
Is there some kind of matching move on the curve side?
Yes, yeah, there is. Yeah, there is, and I'll talk about it. There's. It's a bit complicated to describe like just in one word, but this is exactly what I'm going to talk about. Yeah, I mean, the amazing thing that, well, I guess we'll get to later is that, you know, this kind of so for a large class of coefficients that are called semi-simple, I mean, you can get all of them by just applying the given action to kind of the trivial one or some copies of the trivial one. And so that structure is kind of exactly reflected on the spectral curve side. So. Of those two? Oh yeah, that's a great question. So yeah, that's a great question. Yeah, let me say the advantage of using the spectral curve kind of point of view. Well, there's a few. So first of all, you can sort of use a lot of the kind of geometry of the curve. So I don't know, for instance, you can have a family of curves, right? So you might have some parameter that's kind of moving, and you can ask like what happens to the differentials or to the SFGNs when you kind of move these parameters, right? And then because you're sort of just doing some complex analysis, you can kind of understand what's happening with moving these parameters. But on the other hand, I mean, if you just had some Versor constraints that had some parameters in them, I mean, it's not really, like on the representation theoretic side, it's not really clear how you can deal with these parameters or what happens if you, I don't know, for instance, like, let's say you have some parameters and your simple ramification points and they kind of like collide together, right? And in the representation theory side, it's like completely not clear, right? Because I told you, I mean, what should happen is that these kind of Versor constraints should like kind of go and merge together into some kind of W algebra like constraints. But I mean, this is like, I think no one really knows how to do this. But on the kind of spectral curve side of the story, I mean, you can kind of make sense of all of these things. So if you have some family of curves and you want to work with families, it's pretty nice. So that's one advantage of working with this analytic story, so the topological recursion. And maybe another advantage is that, yeah, so, yeah, let's see. Yeah, I'm just thinking about how to say it. So I mean, another advantage is that like, yeah, so you see like a lot of the information. So for instance, right, like we saw, I mean, yeah, I haven't got to it yet, but like you saw for the Hurwitz numbers, it was somehow this expansion at some point, which was like z equals 0, whatever, some random point on the curve, right? And that gave you some interesting enumerative information, so the Hurwitz numbers. But you know, there was like, you could take exactly the same differentials and expand it some other point on the curve. So, you know, like for instance, when we were doing the Witten-Kontsevich thing, I mean, we were expanding it at a ramification point, right? Or like to get these area structures, we were expanding at a ramification point. So that's kind of, you know, that's kind of useful. So that, for instance, you can use that to get a proof of the LSV formula that I'll talk about later. But you don't see any, I mean, so yeah, like the area structure stuff is like somehow restricted in this in the sense because everything is just happening locally around the ramification points. So the only structures that you see are all local around the ramification point. So if you want to deform your curves, you want to do some other things with these differentials, it's much better to use the topological recursion formalism. The nice thing about the area structure story is, I mean, that you have like better control if you want on like some of the kind of algebraic structures because it's some representations of algebras, and people have studied these things, so we know stuff about them. So you can use things that you know about representation theory of W algebras or whatever. So